the main point about this zero-dimensional nanomaterial is the small scale. And of course, the what I call ligands onto the core of the carbon dust, they are really active edge. Finally, the quantum confinement can tell us also that we can improve the properties as a high photoluminescence property if we add, for example, some elements such as sulfur, phosphor, as an example. So, specifically for the carbon dust, this is a class carbon-based nanomaterial that has been discovered in 2004. And it's only in 2006 that the name has been given to this nanomaterial. When the XU and all reported their work, they felt that what we observed by electrophoresis is due to impurity. And this is in 2006 that in Clemson University with Professor XU that they solved this problem in a way that it was not the impurity, but it was a new type of nanoparticles, and that was in 2006. So we can have different type of, when we talk about carbon dust, we may have the graphene one, we can have the amorphous, we can have the graphitic, and finally the carbon nitride, depending on the precursor we are using to have one type of the other nanomaterials. So as you can see on the next slide, that on the next one, we can see that the published article on the last for the last few years increased, I would say, quite importantly, because the citation, as you can see, is impressive. And on the right side, what I mentioned was a different type of, in terms of nanomaterials, in terms of carbon dust, what are the specificity of these carbon dust? First, the carbon core. And I have to mention carbon core even today, 2022, we have some difficulty to know what is going on with the core. What is the material in the core? So we have a lot of hypotheses, but not any experimental detail to prove it. And passivated surface, like for example, polyethylene glycol, polyethylamine. So this is what important depending of the work you want to do, depending of your application. Functionality, the main functionality is related to carboxylic group and also NH2 group. And this functionality, we can use it for ligation, functionalization of the carbon dust. So that means that the main, at the moment, at least in 2022, the main application is really related to therapeutic work, mainly in cancer research, because we can put a drug ligated to the carbon dust. And carbon dust is a very good, I would say, nano carrier. And if you want to have carbon dust really soluble in water, you use for the passivated surface polyethylene glycol. If you want to have carbon dust electropositively charged, you use the polymer PEI. So as I just mentioned, we have quite a lot of different possibility. But this morning I will talk mainly about the three uh, application for the enhancement of the electric effect, the thermoelectric effect, and finally the hybrid rocket fuel. So let's start with the property of the carbon dust and its application. And as you can see, how can we make these carbon dust? So we have two different approach. We have the top-down approach and we have the bottom-up approach. Top-down, when we start with a large molecule or a large system, and we are able to decompose this large system using laser ablation, electrochemical technique, or discharge, we are reduced to the formation of our carbon dust with a size between 1 and 10 nanometer. The other approach is the bottom-up approach. And in my lab, we have used both approach, but mainly the bottom-up approach because we can purify our carbon dust at a very high level, and that's important for reproducibility of the result. So bottom-up means starting with small molecule, and we use ultrasonic, hydrothermal, or microwave pyrolysis to make these carbon dust. So next step, I will show you what is the different type of carbon dust. And again, we have different type of carbon dust depending of the application. It is very important to mention that. The first one, which is the bottom, this is the top-down approach. This is the black carbon dust. So we start with carbon powder, the size of the particle around 100 nanometer, and we solubilize it in the sulfuric acid, nitric acid, and neutralize by NaOH. And finally, we use the, the autoclave to make the carbon dust. And what is important is the purification. The main methodology we are using for purification carbon dust is dialysis to get rid of the impurity, get rid of also of the precursor of the system. So in this particular case, for the this carbon dust, what we call it black carbon dust, we have 5.8 millimole of carboxylic group per gram of carbon dust. That was one of the paper that we has been quite cited because we are the first lab to work with the carbon dust using the carbon powder. Another example, and this is the gel carbon dust, and this preparation is made from bottom-up approach. And as you can see, we use citric acid, ethylene diamine, and the ratio is 1 citric acid for 14, 1 to ethylene diamine, and this is molar ratio. We use pyrolysis, so we heat it 160 degrees centigrade for 50 minutes, and we use a gas to protect, in fact, our formation to make sure that the oxygen will not contaminate our sample. This is the one that I will use in the three applications I just mentioned. And what is the main reason to use a gel? Because of the facility of the preparation. Second, we can produce it with at least 100 gram if we want over 2 days of work, and you can go up to 1 kilogram. That's the main reason. And the first one I mentioned, the black carbon dust, and the third one I will mention about the yellow and the carbon nitride. I mean, in terms of preparation, I mean, you are limited to about 10 milligram, 20 milligram, but it's difficult to have a productivity that is high enough to work with in terms of, I'm thinking about dielectric material or thermoelectric material or the other one, rocket fuel. So that's the main reason that you will see that we're using the gel for these three applications. And if I continue with the different type, this is a yellow carbon dust. And this one is in, again, the bottom-up approach, but using sonication. So we use the citric acid. And by the way, citric acid is very popular for application in terms of forming carbon dust. And we add the 1,2 phenyl Again, the ratio is important, 125. Solvent, we use water because sonication, like as you know, microwave is important for the reaction. And finally, 1 hour sonication, we got the yellow carbon dust, which has specific crystallinity in this carbon dust compared to the two other I mentioned. The third one is carbon nitride dust using the urea and citric acid. We use also, instead of urea, we use urea, but we have the same property for this type of carbon dust. And we published with this formation of carbon dust in 2019. And the bottom-up approach means we use microwave to make these carbon dust. And by the way, these the molecules, they are very important in photocatalysis, for example, for I would say pollution of water is used extensively. The next one is the one we have done work for 2 years, about 2 years now, to have the red emission of carbon dust. And it's very difficult in a way that if you use molecule of aroma drink, you have a problem. This is very difficult to do degradation of our immune system. For example, chlorophyll will never succeed, flucyanine will never succeed. So dye, this is the one that we have used, the porphyrin. So we're able to see when we use again the microwave methodology to have a look of the carbon dust in the red emission. And I will show you what is the optical property. And we passivate the carbon dust with the PEG 400 for solubility reason in the system. And the next one that we just have in press is related to cationic carbon dust. The application is mainly related to cell biology. So there are not many carbon dust that we can have positively charged. And that's the reason why we have done a lot of work, at least for 2 years, 3 years, to reach this possibility to have positively charged. And I will tell you about the surface of the carbon on the benzene ring. And we use folic acid. Reason is mainly related to the cell biology because folic acid is a good receptor for cells, and we use today. Now the main point is what I mentioned here. This is a few example, and this give you an idea that depending on the application, this is you have really to work on this specific carbon that for the application you want to make. So now what are the different properties that we can measure? So the first one is related to the absorption, followed by the fluorescence spectroscopy, and we finish with the FTR. This is done for all carbon dust. And absorption spectroscopy means for the black, the gel-like, the yellow. So we have been in the mainly in the visible region and a little bit in UV region as around 400 nanometer and crystal at around 320, 325, depending on the carbon dust. This is related to the C double bond C absorption or C double bond O absorption. But this is mainly due to the carbon CO bond that we can observe in the absorption spectrum. The CC band mainly is related to roughly 225 nanometer. That's the one which is at least when we use any aromatic precursor, we will see this band appearing at this wavelength. And for the fluorescence, we have to look the fluorescent normalized fluorescent spectra on the right side. And as you can see, depending of the emission, of the excitation, you have different emission. And this is true for many, I would say, preparation of carbon dust. The one that I just mentioned about the yellow carbon dust at the bottom, as you can see, this is excitation independent. So, but there are not many which shows this independence on the emission spectrum. For those used to using the fluorescence spectroscopy, you know, for all fluorophore, when we have any fluorescence emission, this emission is always independent of the excitation. So in our case, as I just said, yellow carbon dust is independent, but this is rare when we look all the publication in the literature. And finally, the FTRR is to have a look on different functionality on the carbon dust. And we know that the OH group at 300, 3,000, 300 or 3,500 is always due to OH band, but also NH band also. And I don't have time to describe all these spectra, but we can detect for each carbon dust what are the functionality. So the two left carbon dust that we just talked about, the one that give the red emission, of course we have many bands, and in the UV visible region. And as you can see, for the normalized fluorescence spectra, this is really a mix-up Why? Because there are many bands for this dye, and we're able to characterize again functionality on the surface of the carbon dust. And finally, the what we call Y15CD is related to the positively charged carbon dust. And again, this carbon dust is related mainly to the fact that we use 4 amine group connected to the benzene ring, and that's the reason why we have so many bands also in the UV spectrum. And again, for the fluorescence, normalized fluorescence on the insert, so we can see that there is this is excitation, emission, I would say, emission that depending of the excitation wavelength. And we're able to characterize the functionality on the surface. So on the next slide, we have the reason why the in one case on the right side excitation dependent, in the other one excitation dependent. So this is related mainly in terms of hypothesis of the surface state. Some of my colleagues can say, well, we may have formation of also fluorogenic compound that can give emission during the pyrolysis process or the microwave process. Yeah, this is possible, but there is, at the moment at least, I did not see any, at least in many papers, proof that we have formation of the new compounds. So saying that, now we can pass to the last point related to the the analysis of the carbon dust. So this is the X-ray photoelectron spectroscopy, and that gives you the physical technique to know what are your ligand at the on the surface of the carbon dust, and you can see the content uh, in terms of carbon, oxygen, and nitrogen. And there is not much different from one system to the other, except again the yellow carbon dust using sonication to prepare it. The concentration oxygen is important for the black carbon dust. That's the reason why we have the when we look at the carboxylic group of the sulfate, this is quite important. So saying that there is a correlation to terminate with this type of measurement, we have a correlation between the XPS measurement and also the Fourier transform infrared spectroscopy. So this is a very good correspondence between both of them. So saying that, now if we go on the slide regarding the topography, so measure the topography with AFM because the resolution of the thickness is quite resolution quite important. For the temp measurements, well, we use this temp mainly for the XY resolution. And it is a correspondence between the AFM and temp. As you can see for 3 type, the AFM and temp will have a good correlation. For the quantum yield, quite low for the black. For the gel light, that's the one which is very important, 40%. And for the one with the quattro mean 4, initial group on the carbon, on the precursor, I would say, on the benzene, only 1%. I talked to you about the zeta potential. So as you can see for the next 3 that I mentioned, black, gel light, and also the one with the benzene tetra amino group. So we have a zeta potential negative. And if we look on the next slide, so the size of the topography for AFM and TEM, I just mentioned for at least the red, because I mentioned about black carbon dust, also the gel, also for the yellow, but for the red and also the one Y15, so we have a size which is about the same, plus or minus 5 nanometer. And for the zeta potential, that's the one that was mentioned to you for Y15, that they have a positive value of plus 19, but the red one, we got a negative value, minus 18. So the one for the plus 19 is used in I would say, in phototherapy, because we can introduce these carbon dust into the cell line. So on the next one, we start with the enhancement dielectric effect in presence of carbon dust. And as you can see, I have done, first of all, I published this a paper with dielectric constant dielectric material with Professor Costa a few years ago. And I wanted to show you two work work bees with mainly uh, Chaturvedi and collaborator, and one published last year and the one published this year to show you another way to make our carbon dots. In his particular case, he used the paddy, what we call the paddy straw, and make it like a powder, and using the hydrothermal process, 160 degrees centigrade for a few hours, and he produced the quantum dots. Now they introduce quantum dots into the ball mill so that we have a system which is what trap, I would say carbonate is trapped into these stone walls. And what we can is the stone with carbon dioxide, the EMF, and also the DC system. He put the actors and transmittance, but in fact, we can use also the absorbent. We use the absorbent outside, and the peak that he sees is the same that what we have shown for my own preparation my group of the carbon dust. All the gain correspond to our transmittance again correspond to really the compound they have in our system with the stone with nanocomposite. So the next slide gives you an idea about the dielectric. And the first one, a, this is a variation of the dielectric constant. And in both samples, we see this dielectric constant decreasing with increasing the frequency due to the contribution of dipolar electronic ionic polarization and space charge ionization. So the state, waste exhibit a dielectric constant of 55, but the quantum dot or carbon dot stone nanocomposite shows ultra low value of dielectric constant of 10. So at the same frequency. So for the dielectric of pristine epoxy, it was found to be about 5 at the same frequency. So the main explanation is the fact that the nanoscale size and conducting nature of the carbon dust produced and the carbon dust at epoxy stone interface may restrict the dipolar polarization interface region, which may also block the orientation movement of drastic reduction in dielectric constant was achieved. So for the part B, so in this part, we can see the very low dissipative factor of 0.02 for the stone composite and slightly higher toward of 0.05 in case of carbon dot stone nanocomposite. The part C is linked to the AC conductivity of sample. It increases with in the frequency due to the dispersion nature of conducting, and it follows the Joshua Power law relation. So it has to be noted that the carbon dust stone composite exhibit a high AC conductivity as compared to the pristine stone composite at 200 Hertz. So the increase in the AC conductivity with frequency is attributed to the pumping force of the applied frequency that helps in transferring the charge carrier between the different localized states in stone epoxy matrix, as well as liberating the trapped charge from the different trapping center in carbon dust and stone composite. So the figure D is linked to the fluxural strength curve for pristine stone composite shows a strength of 40 megapascal, whereas for the carbon dust reinforced stone nanocomposite exhibit a fluxural strength of 60 megapascal compared to the pristine epoxy of about 33 megapascal. So there is an important increase, which is due to the strong interfacial interchange network bonding of the graphene carbon dust with stone waste particulate and epoxy also resin through dispersion. So the second work that has been published will be brief because I have not much time at the moment. So the principle in terms of preparation on the top one is related to the ball milling, starting with the raw fly ash. And having this fly ash powder, it is introduced into the, the epoxy, and also the carbon dust has been introduced in it too. And this carbon dust has been prepared mainly from paralee powder. Paralee powder is related to what I call a farm culture that we can extract from the farm, and you can use it to make your carbon dust. And using again pyrolysis technique, hydrothermal autoclave, 100, 160 degrees centigrade for 6 hours, we produce the carbon dust. And this carbon dust has been mixed to the epoxy and also the fly ash all together to form a nanocomposite sheet. So the results are shown on the next slide. So for the part A and B, so we can see that the figure shows the variation of dielectric constant with frequency for polymer. And we can see that the dielectric constant increase with the increase of frequency. This is due to the overall contribution of dielectric polarization. And that includes what I mentioned for the last work that has been published on to the electronic dipolar ionic polarization and space charge polarization too. So this rapid increase in the dielectric constant is ascribed to the formation of large electric dipole per unit volume due to the nanoscale size of the fly ash and the carbon dust nanoparticle, and motion of the free charge carrier due to the formation of conduction pathway in the carbon dust fly ash and epoxy. For C and D, dielectric loss of carbon dust reinforced polymer nanocomposite shows the dissipation factor of 7 at high frequency, but only 0.15 for pristine composite at the same frequency. So for the figure E and F, so this it was observed that both nanocomposite increase gradually with increase in applied frequency, and it flows the and it follows it follows the juncture power by relation by the relation. So this part is related to the increase this increase of nano of conductivity, AC conductivity of crystalline carbon dust nanocomposite is explained based on the higher conductivity of crystalline carbon dust compared to the fly ash and epoxy resins. To conclude, for the dielectric, would say, work that has been published this year and last year, so high dielectric conductivity to 350 was observed for the carbon dust nanocomposite compared to 10 for the pristine flash ash composite. The strength of the carbon dust nanocomposite was drastically enhanced by the reinforcement of carbon dust, high fluxural strength of 60 megapascal compared to 35 for pristine. And finally, on the much provide method to increase the dielectric is a mechanical property of nanocomposite by addition of carbon dust is quite important. So the next part is related to, I will try to be short because my time is limited. So the next one is related to the thermoelectric effect. And this thermoelectric effect means that if you have a difference of temperature, the hot side and cold side, you will induce a voltage in your material. So in the next slide, the material we use is mainly the copper selenium. But before to talk about the result, as you can see in terms of potential application, we have something like 50 applications on related to the thermoelectric effect. And what we intend to do when we were using this copper selenium is it possible to increase the thermoelectric effect in this material using carbon dioxide? That's the main idea. So on the next slide. So again, to be brief for each of them, for part A, the figure shows the variation of the Seebeck coefficient as a function of temperature. And we know that Seebeck effect is important because it is directly related to the what we call the figure of merit. If it is high value Seebeck, that means that you have a good figure of merit. If you have a thermal conductivity which is low, that helps to increase the figure of merit. So that's a main point. So this Seebeck coefficient increase with inclusion of carbon dioxide. In figure 5b, we can see the behavior of the electrical conductivity with temperature. A continuously decreasing trend is observed. And that's very important because the figure of merit will be increased in this particular case. In figure C and D, these figures show the change in each thermal conductivity component, electronic and also thermal conductivity. Apart from the simple doped with carbon dust by 2%, so the latest thermal conductivity value were observed to be significantly lower than the electronic thermal theoretical conductivity. For figure E, this figure, it can also be demonstrated that the carbon dust doping alter the thermal conductivity trend from decreasing to increasing over temperature. And low dopant ratio yield with, we would say, with the declining that trend. And again, that means the figure of merit has been improved using our carbon dioxide in each of these figures. So we are used the same concentration in terms of percentage mass weight of the carbon dioxide in the material that copper this study thermoelectric property conversion efficiency of the material by doping with carbon dust. It was conclude also that the presence of carbon nano composite promoter energy filtering effect, which ensure high Seebeck coefficient and low thermal conductivity. So that was important if we want to improve this thermoelectric effect to use the carbon dust a very low percentage. So on the next one, and this is the last application, I would like to mention that we're interested to the rocket fuel, and this is composed of the following. We have a liquid oxidizer and also the combustion for the fuel. And this combustion use solid combustion, and we can use a liquid, but in the work we have performed, we have used the solid. Liquid oxidizer, we use oxygen gas, and the reaction itself is done in the port, and we have an exothermic reaction. This is the combustion chamber that we are using.
Professor Leblanc, you have 3 more minutes.
Yeah, so if I look now at the result of it, so we can go on this figure. So we can see that if we look about this thermal conductivity, and we have the polymer ABS, and we have a paraffin compared to carbon dioxide and paraffin. So this thermal conductivity will have a 20% increase. Figure B is related to TGA, thermogravimetric, and we can see again that the conductivity of the carbon dioxide into the system, the paraffin with 1%, has been improved in terms of conductivity. And finally, for A and B, this is mainly related to the novel fuel compared to the same, I would say, polymer, paraffin, ABS plus paraffin, and you can see the novel fuel give us an average, most important regression rate. And on figure B, in terms of efficiency, so all the curve, the the point of the curve are the experimental one, and the calculated one is the trace one. And we can see that using the carbon dust in our system, so we have 90% efficiency. So this is quite important to increase the combustion rate in the system. And finally, the conclusion is linked to the following point. The carbon dust, this is another class of carbon-based nanomaterial. So we have shown preparation of different carbon dust due to excellent photoluminescence. The carbon that have exhibited potential for photoluminescence in 2D and 3D printing and also fingerprint. The carbon dust have exhibited enhanced effect of both thermoelectricity and de-electricity. And carbon dust are a promising material for making future hybrid rocket fuel. So in the future work to test, we will test the thermoelectricity and hybrid rocket fuel will be repeated with high concentration of the carbon dust. So we can go to the last one, which is related to virtual work that we are working at the moment on the COVID-19 and also on the emission of the carbon dust in the red region. So next slide is a group member, but acknowledgement mainly to those who have done collaboration with my group. And I would like to thank you to listen to my talk.
Okay, thank you very much for your talk. I was checking here this chat mode and I don't see any questions. And in any case, we are already behind our schedule. So thank you, Professor Leblanc, once again.
Thank you.